Okay, good afternoon. In this session, I will be discussing some more examples on shafts of varying cross sections. Composite shafts with varying cross sections. Okay, some numerical examples I will be discussing. I have discussed some of them in the last session. Let me discuss some more examples now. Okay, you see this? The problem reads like this: a shaft ABC of 500 mm length, 40 mm external diameter 40 mm is bored for a part of its length AB to a 20 mm diameter and for the remaining length BC to a 30 mm diameter bore as shown in the figure. So for portion AB, in the portion AB 20 mm hole is bored, and in remaining portion BC it is 30 mm bore, 30 mm dia bore. Okay. So now, if the shear stress is not to exceed 80 megapascals, find the maximum power the shaft can transmit at a speed of 200 rpm. If the angle of twist in a length of 20 mm dia bore, in the length of 20 mm dia bore, that means in this length AB is equal to that in the 30 mm diameter bore, that means in the length BC, the angle of twist is equal in both the parts AB and BC. If it is so, then find the length of the shaft that has been bored 20 mm and 30 mm diameter. So find the lengths of bore holes, the lengths of shaft in which 20 mm bore is made, and what is the remaining length. The total length is 500, isn't it? So if you find one length, that will be sufficient, because the remaining is we can get it. Okay. So how to proceed in this case? Okay. The total length is given, external diameter is given, and internal diameters in AB is 20 mm and internal diameter in BC is 30 mm. And maximum shear stress tau 80 megapascals. Okay, and at a speed of n 200 revolutions per minute. Okay, it is direct application of formulas only. Okay, the torque transmitted by portion AB will be pi by 16 tau into mod IP by D by 2, isn't it? Or the section modulus, actually, polar modulus. Okay, which is given as, actually, polar moment of inertia is given as pi by 32 capital D power 4 minus small d power 4. This is polar modulus divided by y maximum d by 2 divided by d by 2. So it becomes pi by 16 into d power 4 minus small d power 4, isn't it? Yeah, pi by 16 into this one divided by d. Okay. Yeah. Into tau. This is from torsion formula only. Torsion formula. From torsion formula, you will get this. Okay. So substituting these values, external dia, internal dia, and tau value, you will get the torque transmitted by portion AB of the shaft, 942.5 into 10 cube Newton millimeters. Similarly, you can find the torque transmitted by portion BC of the shaft as 687.3 into 10 cube Newton millimeters. Okay. So here everything is same. Internal diameter is different here, 30 mm. Okay. The least of these two will be the strength of the shaft. The least of these two will be the strength of the shaft. Okay. Yeah, the torque transmitted by the shaft is the minimum of the two values TAB and TBC. Okay. So the strength of shaft will be now 687.3 into 10 cube Newton millimeters or 687.3 Newton meters. Okay. So once you know the torque transmitted, you can find the power transmitted by using this expression. P equal to 2 pi nt by 60. Okay. So that gives the power 2 pi n. N is speed in RPM and T we have calculated the torque by 60. Okay. So it gives 14394 watts or 14.39 kilowatts. The power transmitted by the shaft is 14.39 kilowatts. Okay. Now to find the lengths of portions AB and BC. Okay. So here LAB is small l suffix AB. That is the length of shaft portion AB, and L suffix BC is length of portion BC, which is equal to 500 minus LAB. Okay. Now the polar modulus, polar moment of inertia J for portion AB is pi by 32 into capital D power 4 minus small d power 4, isn't it? Yeah, this is the polar moment of inertia for AB and this is for BC. Okay. Now, what is given condition? The angles of twist are equal for portions AB and BC. It is given condition. Okay. So, we know the equation T by J equal to C theta by L, or from which theta is equal to TL by JC. TL by JC. So for portion AB, theta AB is equal to T into LAB by JABC. Similarly for BC, T into LBC by JBC into C. Okay. And what is given is theta AB equal to theta BC. Okay. Theta AB equal to theta BC. Okay. This is BC. Now equating these two and knowing C is same for both because the material is same and torque transmitted is the same. So T and C are same for both the portions. So by equating these two, T and C gets cancelled. You will have LAB by JAB is equal to LBC by JBC. Okay. So LAB by JAB equal to LBC by JBC. And you will get this ratio LAB by LBC ratio equal to 1.37. JAB and JBC are known values only. So you will get the ratio of LAB by LBC. Okay. Also you know that LAB plus LBC equal to 500. So replacing LAB by 1.37 LBC we will get LBC equal to 211 millimeters, and therefore LAB equal to 500 minus 211, that is 289 millimeters. Okay, yeah, that's how we'll find the lengths of the portions AB and BC using the conditions, given conditions. Theta is same for both the portions. Also, torque transmitted is same in both the portions. Okay, for composite shaft, this torque transmitted is the same. Okay, now let us see another example. A composite shaft consists of a copper rod of 30 mm diameter enclosed in a steel tube of external diameter 40 mm and 5 mm thick. The shaft is required to transmit a torque of 0.5 kN meters. Determine the shearing stresses developed in the copper and steel if both the shafts have equal lengths and welded to a plate at each end so that their twists are equal. Here also the condition is given as twist is same for both. Okay, because the ends are welded to a plate at both the ends, and modulus of rigidity is given for copper as well as steel, 40 and 80 gigapascals. Okay, yeah, now better note down the data whatever is given before proceeding to solve. Okay, diameters are given. Diameter of copper rod which is enclosed in steel tube. The internal diameter of steel tube is 40 minus 10. Thickness is 5. So, internal diameter is 30 mm. Internal diameter of steel tube is 30, and diameter of copper rod which is enclosed in it is 30 mm. So, torque transmitted is given 0.5 into 10 power 6 Newton millimeters. It is given as kilonewton meters, 0.5 kilonewton meters. And modulus of rigidity is given. So now let T suffix C is the torque shared by copper rod and tau C is shear stress developed in copper rod. Similarly, capital Ts and tau S are corresponding values in steel tube. That is torque shared by steel tube and shear stress developed in the steel tube. Okay, and the condition here in this case is the torque is shared between the copper rod and steel tube. Okay, in the previous case the torques are same for both the sections of the shaft, but in this case the torques are not same. Torque applied is shared among the steel tube and copper rod. Okay, so the total torque is equal to torque shared by copper rod plus torque shared by steel tube, which is equal to 0.5 into 10 power 6 Newton millimeters. Okay, now the polar moment of inertia for copper rod is given as 5 by 32 d power 4. So what is diameter of copper rod? 30. So you will get this in terms of pi. Let it be like that only. Similarly, polar moment of inertia for steel tube is okay. And from torsion equation, theta is equal to TL by JC. And theta C for copper rod, it is TCL by JC into CC. So TC is unknown, length is known, length is known, length is given, isn't it? Length is not given, but it is same for both. Okay, so TC into L divided by JC into CC. We have to be careful about units. We have to convert all of the units into single system of units only. Okay, we have to convert this is 40 gigapascals actually. So it is converted into megapascals, multiplying by 10 cube. Megapascal is nothing but Newton per mm square, and this is JC is in mm power 4. Okay, yeah, we have to take care of units before substituting the values. Similarly, theta s, that is angle of twist in steel tube, is given as TSL by JS into CS. So TSL divided by this much. Okay. The condition is theta c is equal to theta s. Okay. So now we equate this theta s to theta c, which gives L cancels. Okay. Which gives TC in terms of TS. Okay. Now we substitute this in this expression. TC plus TS equal to 0.5 to 10 power 6. Okay. So from this you will get torque transmitted by steel tube, which is 0.406 into 10 power 6 Newton millimeters, and TC is 0.5 minus 0.406, that is 0.094 into 10 power 6 Newton millimeters. Okay. So now we find the torques shared by each of these. Now we will find the shear stress in copper rod as well as steel tube. Okay. Knowing torque equal to pi by 16 tau c into dc cube. Okay. Yeah. Tau c we need to find. DC is known 30 mm. So substituting these values, you will get tau c as 17.7 Newton per mm square. That is megapascal. Similarly, in steel tube, TS equal to pi by 16 TS into this one, ds power 4 minus small ds power 4 by ds. Okay. Actually, pi by 16 into this is polar modulus. Okay. So substituting the values, you will get tau s, the shear stress in steel tube. Shear stress in steel tube. Okay. Yeah. This is one type of problem. Okay. So based on the data given, we have to proceed. Okay. One more example we'll see. A composite shaft consists of a steel rod of 60 mm diameter surrounded by a closely fitting tube of brass. Find the outside diameter of brass tube when a torque of 1 kN meter is applied on the composite shaft and shared equally by the two materials. Okay. Take C for steel 84 gigapascal, that for brass is 42 gigapascal. Also determine the common angle of twist in a length of 4 meters. So length of shaft is 4 meters. So diameter of steel rod is given, and inner diameter of brass tube will be the same as that of the diameter of steel rod. And total torque is given, and which is shared by steel tube and copper rod, steel rod and brass tube, isn't it? They share the torque equally. That means the torque shared by brass tube is 0.5 into 10 power 6 Newton millimeters, and also that shared by steel rod is 0.5 into 10 power 6. Okay. half of 1 into 10 power 6. Okay, modulus of rigidity for brass is given, that is C. This is not sigma. CB is 42 and that for steel is 84 gigapascals converted into megapascals multiplying by 1000. Okay, and length of shaft is 4 meters. So this is the data given. So how to proceed now? So we find the modulus polar moment of inertia for a steel rod, okay, and also for brass tube. Here we don't know the external diameter of brass tube, okay, we need to find that. Angle of twist is obtained by using this expression, okay, so which is TL by JS into CS, okay. Similarly, theta B is this one, okay, and what we know is the angles of twist are same, okay, angles of twist are same for both, is it? In the previous problem also we have seen angles of twist are same, theta S is equated to theta B, okay. So TL gets cancelled here and the only unknown we have is dB, which is obtained by solving this as 79 millimeters. 79 millimeters. Okay. The outside diameter of brass tube is 79 millimeters. And what is the common angle of twist? Common angle of twist. So you can find by substituting this value of dB here. Okay. So you will get angle of twist as 1.07 degrees. Okay. 1.07 degrees. Yeah, that's all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.